Alright gang, here we go. This is for Chem 2 Unit 8. Today we're talking about vapor pressure. We're talking about phase diagrams and liquid crystals. Alright, so first of all I want to go back to this diagram. This is from PhET, from their little states of matter diagram here. And I've got it set up so we're going to be looking at water at its liquid state. Okay, so we'll hit go. Now I want to look at something here. We know already that these water molecules, they're semi-arranged with their hydrogen bonds, but there's a little bit of them that are kind of, that are unorganized perfectly. Like if we go to solid, that's gas. If we go to solid, we can see that we form these mostly hexagonal structures in here. Okay, and as we cool down the temperature, we get more and more of these solid hexagonal structures showing, and that's all because of those hydrogen bonds they make. Now, if we jump to the liquid, they move around past each other more, and that makes sense because it's a liquid. And if we go to gas, they're spread out a lot farther from one another. All right, so here's a gas, or liquid, excuse me. So you can see that these water molecules have a kinetic energy. All of them are spinning or bouncing off each other. Now notice that these two guys up here, and now starting to be this guy, they're separated. They have a lot less or a lot more distance between them and the other water molecules. And the reason for that is that they've developed enough kinetic energy just from pure collisions and pure randomness that they've been able to distance themselves from the other water molecules and been able to break free of those intermolecular forces. And as we watch this, we can see this happens every once in a while. Every so often, one at the surface will just happen to get enough kinetic energy that it's going to go up and become in the gas state. Now, we define something that's in the gas state, like these two guys here, even though we're at liquid temperature, these are vapor particles, okay? These are vapors, all right? So these molecules of water that are up here, all right, that should be liquid, but they have enough kinetic energy to act like a gas. We call them vapor. And so they form this new thing we're talking about today called vapor pressure. And essentially, vapor pressure is the pressure exerted by the vapor molecules of a liquid on that liquid. Okay, so we can actually increase the vapor pressure by making us have more vapor molecules simply by increasing the temperature. If we increase the temperature, there's more kinetic energy, right? There's a higher average kinetic energy, so we'll end up with more molecules able to gain enough kinetic energy to go past. So notice that we're pretty close to the boiling point, or we're way past the boiling point, so a lot of it should be boiling by now. All right, so maybe we'll cool it down a little bit. So we're just past. So that's like right at the boiling point. So if we're at 273, oh yeah, we're still way past boiling point. But anyway, so you notice that as we increase the temperature, we have more and more of these molecules that are able to escape into the gas phase, so on and so forth. All right, so this brings us to this idea of the vapor pressure, okay? So really, this is kind of the generic idea. If we're at any temperature, there are always some liquid molecules, and this is at any temperature. Okay, there are always some liquid molecules that have enough energy to escape the surface of whatever liquid, to escape that surface tension. Okay, and become a gas. Okay, and so, like, for example, if we have this thing here, and we'll just pretend this is water. It doesn't really matter what it is. Remember, so we talked about curves, these bell curves before when we talked about kinetic movement. We talked about average speed, URMS, stuff like that. Okay, so these are a fraction of molecules. The blue curve is when we're at a lower temperature, and the red curve is the higher temperature. Notice that if you imagine we found the area under both of these curves, they would be equal to each other. The area under the blue curve and the area under the red curve. Okay, now, but the difference is that this dotted line, this is the minimum kinetic energy needed to escape. So this is the amount of energy something needs in order to break those intermolecular forces completely and become a gas. And so notice that when we're at a higher temperature, we still have molecules that are relatively not moving, but there are more molecules that have enough kinetic energy to escape. So there's a lot more. There's probably double the energy here, even though the average, has only gone up just a little bit, okay, from here to here. About the same, really. Anyway, and so as the temperature rises, we'll still have molecules that are moving, relatively slowly, but a higher fraction of them will be able to escape into the gas. And so as we continue to grow our temperature, as our temperature increases, more and more of our molecules will be able to escape the intermolecular forces and act like a vapor as a gas. Okay, so as more molecules escape the liquid, the pressure they exert increases. Okay, and remember, pressure is defined as the force over the area, so this is the force of those molecules hitting the side of your containers and the surface of the liquid. All right, and so as that pressure increases, okay, what's going to happen is you'll have more and more of these molecules escaping into the gas phase. So imagine we have some container here, right? Okay, and you've got molecules in here, okay, and then one or two of them hit up, and you can imagine, like, well, when these two guys are up here, okay, if they happen to hit each other hard enough, they'll, one of them will lose their kinetic energy, and then that one would have to drop back down. And then what would we call that? Well, that would be condensing, right? And so the ones down here that have enough energy to escape, they would evaporate. Okay, these guys would evaporate, and then the ones up here that slow down, that no longer have enough kinetic energy to break those intermolecular forces, they would condense. And eventually, if you let it sit for long enough, and it doesn't take that terribly long of a time, you would reach a point where both the condensation and the evaporation are occurring at equal rates. So you've got these liquids, they're evaporating, going up here, and you've got condensation occurring. And you kind of get this cycle going where these two rates are equal to each other. And we call that, when that occurs, dynamic equilibrium. Okay, dynamic equilibrium. All right, it's equilibrium because from a macro view, the amount of molecules that are in the gas state and the amount of molecules that are in the liquid state are remaining constant. Right, we've got an equal number. If you took a snapshot, one time and then another time, and once you've reached equilibrium, you should have the same number of molecules in the gas state in both times, or in the liquid state in both times. But we call it dynamic because it's constantly changing. It doesn't stop evaporating and condensing. They just have reached a point where those rates of change are equal to each other. Okay, and so that's really what we mean by dynamic equilibrium. This is a really important concept to understand, and just know that equilibrium, we're using this as really our first example of equilibrium, but we can have equilibrium systems established in all sorts of conditions. We'll spend an entire unit or two towards the end of the year talking about equilibrium, how does it occur, in chemical reactions, so on and so forth. Okay. Now, let's talk about, well, what does this have to do with boiling real quick? So we've talked about evaporation, so let me grab a blank screen here, white screen. So if you imagine, again, if we have a beaker, okay, and in that beaker we've got water and you've got heat, right? We're producing heat down here. Now, when you produce heat, right, we had talked about how, just a second ago, that evaporation occurs when molecules escape from the surface, right? The entire liquid here is just a bunch of molecules that are squished together, so on and so forth. And up here at the surface of the liquid, you've got these water molecules, and they'll get hit from below, and that'll allow them to escape and bounce up here into the atmosphere. But at the same time, down here next to the heat source, these molecules are also gaining heat, but they can't escape, right? So they kind of get stuck in the middle, but they still have enough kinetic energy to become a gas. So what they do is they kind of form a bubble, right? So they'll form a bubble, okay? And this bubble has gaseous water molecules in it if we're using water. And so because they're gas, they're going to be exerting a pressure, right? Well, everything exerts a pressure, but these gas molecules are going to be exerting a pressure on all sides of their bubble. And that pressure is equal to the vapor pressure, right? Because it's the vapor of that water, so it's going to be vapor pressure. So that vapor pressure is pushing against the sides of the bubble, okay? Now, here's the interesting part. We know that at the same time, there's atmosphere pushing down on the surface of the water. Okay, so there's atmosphere pushing down on the surface of the water. If this vapor pressure is less than the pressure of the atmosphere, then our bubble gets squashed. Okay, if this pressure, the vapor pressure, is less than this, okay, because this is pushing down, if our vapor pressure inside this bubble is less than the atmospheric pressure, then the bubble cannot exist. It gets squashed. Okay, but if those molecules have enough kinetic energy that they can hit the outside of the bubble or the inside of the bubble hard enough that pressure is equal to the atmospheric pressure, then this bubble will be allowed to live. Okay, so we'll have a live bubble. Okay, that is allowed to exist. And because this is a gas, it is less dense than the liquid, it will rise to the top and it'll eventually bubble out and you'd get gaseous water vapor up above. Now that should sound really familiar if you've ever made spaghetti or macaroni or ramen noodles, that you've seen this occur. Water, that you'll see bubbles start to form at the bottom and they might exist and then go away and then exist and then go away. And eventually they reach the point where they exist and they're able to come up towards the top. And we call that boiling. Okay. So boiling, okay, is really the boiling point is when the vapor pressure, okay, of whatever liquid you're talking about equals the atmospheric pressure. Okay. So what this means is really that we can make anything boil at any temperature. Okay, all we have to do is reduce the pressure enough that the vapor pressure is equal to the atmospheric pressure. All right, and in class we probably busted out the vacuum pump and lowered the pressure inside of the bell jar so that we can make the water boil at room temperature. Pretty wild, okay? And so so this is a really important idea about what boiling is. A lot of people assume boiling only occurs when it's hot, but really your boiling can occur at any temperature. Okay, you just have to control the pressure because it's not about the temperature. It's about the vapor pressure equaling the atmospheric pressure. All right. Normal boiling point is the temperature at which you boil if your vapor pressure is 760 torr. It's essentially what temperature do you need to get to so you have 760 torr. Remember, this is the same as 1 atmosphere. Okay, so normal boiling point, 1 atmosphere. All right. So here's the normal boiling point of several things. Water is at 100 degrees Celsius. We've defined that. That's really nice. Ethanol or ethyl alcohol is at 78.3. All right. Diethyl ether is 34.6. Ethylene glycol is way out here. I should have looked it up. I'm kind of curious now what the boiling point is. But anyway, or the normal boiling point. Okay. Another interesting idea is if you, just out of curiosity, if you took the natural log of the vapor pressure and set it inversely proportional to its temperature. So you take your natural log of your pressure in your y-axis and then took the temperature that was related to that value and inversed it and then graphed it, you'd get a straight line, and this would be the slope. The slope would be, it would be a negative slope, and it would be the delta H of the vapor pressure over the R value, and that R value is the constant. Okay, now this relationship occurs for everything. It's pretty wild. We always get a straight line if we graph these guys together. Okay, and this formula can be, there's lots of different versions of this formula, but they all essentially say the same thing. It's this Clapeyron, I'm not quite sure how to say that, Clapeyron equation. All right, and this is kind of what exists. Like, there's probably a couple textbook problems that I'll ask you to do solving with this, but essentially what I really want you to know is that this equation allows us to estimate the vapor pressure at another temperature. Okay, as long as we know the vapor pressure at a specific temperature. So if we can figure out one temperature vapor pressure relationship, then we can solve for any temperature vapor pressure relationship. So that means if we can find the vapor pressure at room temperature, we can use the Clapeyron equation to figure out what the vapor pressure would be on the surface of Mars or under the ocean, or whatever we want. Okay, and so this is really super handy. Okay. All right, so a couple of practice problems here. It shouldn't be too difficult. It says, in the mountains, water in an open container will boil when its critical temperature exceeds room temperature. Well, that's just silly. We're not saying anything about critical temperature. Okay, its vapor pressure equals atmospheric pressure. Well, that should sound really familiar. That is the definition of boiling. So that's got to be at least one of the answers. Let's check the others, see if there's more than one. Its temperature is 100 degrees Celsius. Well, it should be past boiling at 100 because this is the definition at normal atmospheric pressure. Okay, so technically it should be boiling, but that's not quite the best answer. B is better than that because we're going to boil before we reach 100. In fact, if we reach 100, we won't have any liquid left at all. Remember our heating curves. Remember our water cannot get hotter than its boiling point until it's no longer a liquid. All right, and then enough energy is supplied to break covalent bond. Well, this isn't, boiling is a physical change, so that means we're breaking intermolecular forces. Breaking covalent bonds would be a chemical change, so that's just silly. And then none of these correct. Well, that's just not true. We already said that B was correct. All right, so B is the answer on that one. It says, use figure 11.25 to determine the external pressure if ethanol boils at 60 degrees Celsius. So let's jump back here. So this guy here says ethanol at 60, and we want to know the pressure. So this would be the yellow line, orange line, whatever color this was. That's ethanol at 60 degrees. So this occurs about, what, here? So that's what, 325 torr or so? Easy enough. Let's write it down just for fun. 325 torticelli. All right. Phase diagrams. All right, phase diagrams, we probably learned about this in Chem 1, but let's just recap here. Phase diagram is a graph showing the states of matter under conditions of temperature and pressure. Okay, so we always put pressure on the y-axis, temperature in the x-axis. Pressure is almost always in atmospheres, but it can change. Temperature is usually always in Celsius, but it can be in Kelvin. Depends. Okay, there's a couple of things you always need to know. Solid is always on the top left portion, gases are always on the bottom right portion, and liquids are always in the middle. So it always kind of makes this shape like this. This phase diagram here is like an example phase diagram of about 90% of what molecules look like. Their phase diagrams. All right, when we are on these lines right here, we are at dynamic equilibrium. Okay, so if we exist right here, if we're at the specific temperature and pressure that we're right here, okay, that means our sublimation and deposition are occurring simultaneously. They're both happening at the same rate, right? But if we're off this line, that means nothing, that it's still sublimating and depositing, but deposition happens much more quickly. All right, so the most of our molecule will be in the solid state. All right, okay, and so we can kind of figure out just by, if we know pressure and temperature, we can easily tell what state of matter would be most abundant. Okay, we could also say, like, well, what if I start here at this phase and then I start heating it up at constant pressure? Well, we're going to go from solid to liquid. We'll melt it, and then eventually I'll liquid and we'll boil, right? And we'll vaporize it, okay? And so you should know that, well, between solid and gas, we go sublimate and deposit, and then liquid to gas, melt and freeze, and then vaporize and condensate. Okay, a couple other good important points. The triple point here, triple point is when all phase changes are at dynamic equilibrium. All right. So right here, this is the triple point. All phase changes are at dynamic equilibrium. That means we have solid turning into a gas, solid turning into liquid, liquid turning into solid, gas turning into a liquid, or solid, gas, liquid to gas, gas to liquid, all equally happening at the same rate. There's some really cool videos out there of different people being able to make different things that hit their triple points. A lot of times it's kind of tricky because you have to be fairly cold and at a fairly low pressure, and you kind of got to be able to hold it there. And you can. It's pretty cool though because you can see solid and liquids and gases all happening. So it'll be boiling, freezing, and melting all at the same time. Those are the three that are kind of easy to see what's going on. All right, the other point is this critical point. We talked about this a couple of slides ago. Remember that we've got this imaginary, or not imaginary, we got this like little dashed line here and another dashed line here. And when we're past this region here, where this is called, we're a supercritical fluid. And this is where we we have a liquid that acts like, or really it's more like a gas that has certain properties of a liquid is a better way to look at it. And remember, this occurs when we're past, this would be called the critical temperature. And then this over here would be the critical pressure. All right, and so we've got this point over here. Okay, all right. So phase diagram of water. So remember, this is the normal one. Kind of take a gander at like what's going on here. You got a kind of curvy here, and your line, you kind of align with a positive slope. Water is super weird for a couple of reasons. Number one, it's got a ridiculously high critical point. Okay, especially for its size. Water only weighs 18 grams per mole, and so it's like, whoa, it's got a really high critical point. And most of that is because of the dipole nature of water. The hydrogen bonds are also helping out quite a bit. Okay, the other super weird thing that goes on is notice that between solid and liquid here we have a positive slope, and then between liquids, or between water, solid, and liquids, you actually have a negative slope. It's kind of slightly veers to the left and gets a little sharper to the left. Essentially what this is saying is that as you increase the pressure, that you can actually, if you had a chunk of ice at 0 degrees Celsius, right? It should be at, we're at atmospheres, so 1 atmosphere would be somewhere around here, right? So you'd have, let's see, 0.0063 atmospheres. So it'd be like somewhere around here, right? This is kind of a little bit funky. Anyway, so you should have a solid at 1 atmosphere, 0 degrees Celsius. We should be at, if we're right at 0, we should be right on this line. So it'd be like a 1 atmosphere. Shoot, why am I down there? You guys are thinking I'm nuts. All right, so here we are, okay? So if you took this guy, held the temperature steady, and increased the pressure, okay, your water, any solid ice you had would actually get pushed over to the liquid, because you can see that because we have a negative slope here, that once we're up here, if we're at 0 degrees Celsius, and say we get to 100 atmospheres, we'll be in the liquid area right there. Okay, and you can see that as we increase our pressure, we'll actually start melting. And the reason for that is the same thing that we talked about earlier, is water tends to form these hexagonal structures, and they're less dense. They spread out, right? Water, solid ice floats in water. It's less dense than water. And so as it spreads out, these ice chunks, okay, take up more space. Now, if we increase the pressure, really we're making that water get closer and closer to one another. And so as it gets closer and closer to one another, because liquid water is more dense than ice or than solid water, that it's going to take up less space, and that's what makes it melt. Kind of bizarre. Okay, here's carbon dioxide. A couple of interesting things. Carbon dioxide is pretty fascinating. Okay, notice that if we're at 1 pressure or 1 atmosphere, which is about what we exist at, if you take a piece of dry ice, remember that's solid carbon dioxide, right? If you take a piece of dry ice and pull it out of its freezer, I believe they keep it at like 150 degrees, negative 150 degrees Celsius, so it's somewhere around here or so. And then as soon as you take it out, it's going to start warming up, because we don't live that cold. That's stupid. Okay, that's cold. Okay, and so we're going to let it's going to start taking heat, and heat is going to flow from the surroundings of the dry ice back into the dry ice. And so this heat comes in towards your dry ice, and so your dry ice is going to start gaining heat, so that means it's going to travel this way. Now notice that there's no liquid state here in order to get it to convert from the solid to the gas. So as heat comes in, all right, as heat comes in, we don't go to the liquid phase at all, and that's why dry ice completely bypasses its liquid state, and that's why a dry ice is like the #1 example people get when we talk about sublimation. Okay, and it's all because of this crazy idea that carbon dioxide cannot exist as a liquid below this pressure. Okay, notice that this is your triple point, and it's at about 5.11 atmospheres is what they say. Okay. 2, 3, 4. I don't know about that. I guess it's logarithmic. But anyway, and so we can kind of see. So below triple point, we can't get that. So that's why CO2 sublimes at normal pressure. All right, let's try a couple of practice problems here. So it's based on the phase diagram for methane. What happens to methane as it is heated from negative 250 to 0 degrees at a pressure of 10 to the negative 2 atmospheres? So we're at 10 to the negative 2 atmospheres, and we're going from negative 250. So where are we at? We're like somewhere over here, and to 0 degrees. So going from here to here. Okay, so we're going to increase until we hit about, 200 degrees. So we're going to sublime, because we're going from solid to gas. So we're going to sublime at about negative 200 and then heat up. So let's see, sublime's at about negative 200. Well, it's not melting because it's not turning into a liquid. It's not boiling because it's not a liquid to start with. It's not condensing because that's the wrong way. It's not triple point because that's at 10 to the negative 1 atmospheres. So it's got to sublime at negative 200. Pretty easy. All right, let's try this. It says, what is the use the phase diagram of methane to answer the following questions. What is the normal boiling point of methane? So normal boiling point, remember, is at 1 atmosphere, and we're going from liquid to a gas. So normal boiling point would occur right here. All right, so let's see, what would that be? So like 180, negative 180 or so. Okay, over what pressure range does solid methane sublime? Well, that occurs from about, 10 to the negative 1 pressures, so 0.1 atmospheres and below. Okay, over what pressure range does solid methane we just answered. At what temperature does the liquid methane not exist? Anything past the critical temperature. So that would be negative. Let's see, above what temperature does liquid methane not exist? All right, so that could be about 4. I don't know. It's kind of hard to tell. It's like negative 80 degrees or so. Okay. Last little bit here is these crazy guys, and this is a pretty new field of chemistry, are these ideas of liquid crystals. Okay. Liquid crystals are substances that have kind of an in-between state between the solid state and the liquid state. All right, and we call these liquid crystals because they're sort of crystallized, but they also have some still some liquid motion to them. Okay, so they got some liquid properties and solid properties. Okay, and so essentially these liquid crystals have some degree of order, and we've developed all these different words to kind of help us describe it. So for this specific compound this is, I'm not quite sure what it is. Below 145 degrees Celsius, it's a solid, but between these two here, we've entered a liquid crystalline phase. All right, and then above 179, it's back to a liquid. Notice that it's kind of translucent here, and then past that is completely transparent. Well, completely transparent. It's more transparent. How about that? All right. So here's the different types of liquid crystals that are mentioned in our books. Okay, in pneumatic liquid crystals, molecules are ordered in only one dimension. So here's their liquid phase. These guys are kind of pointed whatever direction they want to be. Okay, pneumatic crystals, notice that they're all oriented along this y-axis, just up and down. They're essentially all organized this way. Okay, smectic crystals are ordered in two dimensions. Okay. Number one along an axis, so notice these guys are all along the y-axis, but they're also in layers. So you got a layer 1 and a layer 2. All right. You also could have a smectic crystal that looks kind of like this, where you've got your axis, and they're not necessarily perpendicular to one another. So you got this other axis that's kind of at an angle like this, and then but you've also got separate layers. And then finally, your cholesteric liquid crystals, you've got these totally different layers, and they're all organized different. Along different axes, so they're kind of at specific angles to one another. So it's kind of interesting. Okay, and all of these have kind of different applications. All right, this is kind of a new field of chemistry. It has a lot of exciting applications and so on and so forth. All right, so that's it for chapter 11. Okay, we talked about vapor pressure, phase diagrams, and liquid crystals. Let me know if you have any questions, and I'll see you on the flip side.